This is a review for Chapter 7, Math 1050. Let's go ahead and get started. The first problem, we're asked to state the first four terms of the sequence 2n plus 3 over 4n from n equals 1 to infinity. Here our general term is a sub n equals 2n plus 3 over 4n. We start by finding a sub 1, where we set n equal to 1. A sub 1 is going to equal 2 times 1 plus 3 over 4 times 1. And we simplify to get 5/4. Our second term, we set n equal to 2, and we have 2 times 2 plus 3 over 4 times 2. We simplify to get 7/8, it looks like. And then we move on to a sub 3, where n is equal to 3 in our general formula here. And we have 2 times 3 plus 3 over 4 times 3, which simplifies to 9 over 12. A sub 4, where n is equal to 4, 2 times 4 plus 3 over 4 times 4, and we get 11 over 16. So we have 5/4, 7/8, 9/12, which we could simplify to write that as 3/4 if we wanted, and then 11/16. And we could keep going, but we were only asked for 4 terms here, so let's call this good. Note that this has the look of an arithmetic sequence, being that in the numerators we go from 5 to 7 to 9 to 11, and in the denominators we go from 4 to 8 to 12 to 16. But if you actually take a look for going from term to term, to go from 5/4 to 7/8, that would be going from 10/8 to 7/8. We would subtract 3/8 to go from the first term to the second term, and then to go from the second term to the third term, we'd go from 7/8 to 3/4. 3/4 is the same as 6/8. So 7/8 to 6/8, we'd subtract 1/8, and I wrote that incorrectly. 5/4 to 7/8, we subtract 3/8. Anyway, these numbers are not the same, so we do not have a common difference here. So we can see that this would not be an arithmetic sequence. Let's go on, and we will get to a bunch of arithmetic sequences soon here, but for this one, it did not tend to be so. So let's go on. And in problem number 2, we state the first 4 terms of the sequence. A sub 1 equals -3. A sub n equals 2 times a sub n minus 1 plus 3. We already have our first term given to us. A sub 1 equals -3. So we move on to find a sub 2 by setting n equal to 2 in our general formula there. So if n equals 2, we have a sub 2 equals 2 times a sub 2 minus 1 plus 3. We just plug in 2 for n wherever an n appears here. That simplifies to 2 times a sub 1 plus 3. We know that a sub 1 is -3, so we have 2 times -3 plus 3. That would be -6 plus 3. We then will write a sub 2 as being equal to -3. For a sub 3, we plug in 3 for n, so we have 2 times a sub 3 minus 1 plus 3, or 2 times a sub 2 plus 3. A sub 2 was -3, so we can write this as 2 times -3 plus 3. Simplifying, we get a sub 3 equals -3 again. Now, I'll bet you can guess what a sub 4 would be, but let's go ahead and work it out through the formula. Setting n equal to 4, we have 2 times a sub 4 minus 1 plus 3, which is 2 times a sub 3 plus 3. A sub 3 was -3, so we have 2 times -3 plus 3, and we end up with a sub 4 being equal to -3, and we have our first 4 terms. The sequence would look like -3, -3, -3, -3, and so forth. This sequence, you could think of being arithmetic if you thought of your common difference as being equal to 0, or you could think of this as being geometric if you thought of your common ratio as being equal to 1, where we would multiply by 1 each time we go from one term to the next. So think about that, but for now, let's go on to problem number 3, where we state the nth term of the sequence. We have 1 4/3, 9/5, 16/7, and if we write these all as fractions, which I would want to do to kind of see what's going on, I would probably write this as 1/1, 4/3, 9/5, 16/7, and then I would just start glancing at this for a bit and seeing what's going on, if I can notice any patterns here. Well, one thing I noticed right off is the numerators are squares. So the first numerator of 1 would be 1 squared. The second numerator would be 2 squared. The third numerator would be 3 squared. And the fourth would be 4 squared. So that's looking promising. And we still have 1, 3, 5, 7 in the denominator. So let's think of those denominators a little bit more. Well, one thing I might look at the denominators. If I have 1, that would be what? That would be 1 plus 0, right? So we could think of this first denominator as being 1 plus 0. The second denominator would be what? 1 plus 2. The third would be 1 plus 4. And the fourth would be 1 plus 6. Sometimes this doesn't go anywhere when we just start thinking of what might be, but let's go with it. So we have 1 plus 0, 1 plus 2, 1 plus 4, 1 plus 6. Well, each of those is a multiple of 2, right? So we could think of 1 plus 0 as being 1 plus 2 times 0. We could think of 1 plus 2 as being 1 plus 2 times 1. 1 plus 4 would be 1 plus 2 times 2. 1 plus 6 would be 1 plus 2 times 3. So we have something going on here. And then look at what the terms are. Our first term would be a sub 1. Our second term, a sub 2. Then a sub 3, a sub 4. Okay, so somehow if we can get these numbers 1, 2, 3, and 4 in here, we're good. Let's see. So let's look at, if we have 1 plus 2 times 0, 0 would be equal to 1 minus 1, right? 1 would be equal to 2 minus 1. 2 would be equal to 3 minus 1. 3 would be equal to 4 minus 1. So let's see if we can come up with a general formula here that would work for any term. We're going to start with our, whoops, sorry about that. Let me go back. We're going to start with our numerator, which is easy enough. 1 squared, 2 squared, 3 squared, 4 squared, where n equals 1, 2, 3, 4. So we could just write the numerator as n squared and go on then to the denominator, where we can see that we have 1 plus 2 times something. Well, to get that something, notice that if I look at what n is each time, I could just take n minus 1, and it looks like that would work. So let's just check out a sub 3. Let's see if this works for a sub 3. So for a sub 3, I'd take 3 squared over 1 plus 2 times 3 minus 1, and that would give us 9 over 1 plus 4, or 5. So 9/5, that is our third term, and I think if you tried the other ones, you would see those work as well. Okay, so we have it. We have a formula for a sub n squared over 1 plus 2 times n minus 1. Let's go on to problem number 4 here, where we want to state the 8th term of the geometric sequence. We're told that this is geometric, so that saves a little bit of work. Well, if we want to state the 8th term of the geometric sequence, I'm going to start by trying to figure out what a sub 1 is. That's easy enough. Our first term here is -3. And then I want to figure out what our common ratio is. Well, what do I multiply -3 by to get 1? One way to figure that out is to take 1 divided by -3, and that would give us our common ratio of -1/3, which you can go ahead and try, and you can see that each time we go from one term to the next, we basically multiply by -1/3. So our common ratio is negative 1/3. For the 8th term of the geometric sequence, I'm going to use a formula to find that. The formula for the nth term would be a sub n equals a sub 1 times r raised to the n minus 1, where here we have our first term is negative 3, our common ratio is negative 1/3, and that's raised to the power n minus 1. So if we want to find a sub 8, we're just going to plug in 8 for n, and we have negative 3 times negative 1/3 raised to the 7th power. So a negative number raised to an odd power is going to be negative, and I'm going to have negative 1 over 3 to the 7th power, and 3 to the 7th power then would be 2,187. So negative 3 times negative 1 over 2,187, we get our 8th term is equal to positive 1 over 729. All right, so let's go on to problem number 5 here. Find an explicit formula for an arithmetic sequence such that a sub 5 equals 8 and a sub 15 equals 78. Okay, so our general formula for a term a sub n in an arithmetic sequence is going to be a sub 1 plus n minus 1 times d, where d is the common difference. So we need to figure out what n is, or we need to figure out what a sub 1 is and what d is, right? We have we're told two different things here. We're told, first of all, that a sub 5 equals 8. Well, if we just start by writing what a sub 5 would be, according to our general formula here, a sub 5 would be equal to a sub 1 plus 5 minus 1 times d, or in this case, we do happen to know that a sub 5 is 8. Oh, I just messed up, so let's try that again. Let me see if I can go back to this slide. Sometimes it throws me out. Okay, I think we're good. Let's keep going. So a sub 5 is 8. So here 8 is going to equal a sub 1 plus 4d. And then if we look at our 15th term, we know that a sub 15 is equal to 78. Well, a sub 15, according to our general formula here, would be a sub 1 plus 15 minus 1 times our common difference. We're told that a sub 15 is equal to 78, so we have 78 equals a sub 1 plus 14d. Again, we're trying to find what d is and what a sub 1, our first term, is. Well, if we add these together using the elimination method, I can start by writing 78 equals a sub 1 plus 14d. And then if I multiply my other equation here by negative 1 on both sides, I have negative 8 equals negative a sub 1 minus 4d. I'll add these two equations together, and we have 7d equals 0 plus 10d. That gives us d equals 7. Okay, so we've got d equals 7. We still need to find a sub 1. That's easy enough to do. If I pull down this 8 equals a sub 1 plus 4d and plug in 7 for d, I have 8 equals a sub 1 plus 4 times 7. We get 8 equals a sub 1 plus 28. Subtracting 28 from each side, I'm going to get negative 20 equals a sub 1. Okay, so we have a sub 1 and d. We can then find our explicit formula, going back and grabbing our general formula for a sub n, and we can write a sub n equals a sub 1, which we found to be negative 20, plus n minus 1 times our common difference of 7. And so we have a sub n equals negative 20 plus 7n minus 7, or just simplifying this, a sub n equals 7n minus 27. Okay, and you could check that if you wanted to make sure that works for our 5th term and for our 15th term, and it should. But go ahead and try that on your own, and let's go on to problem number 6. Here we want to determine whether the sequence is arithmetic, geometric, or neither. We have 100, 20, 4, 0.8. I can pretty much see right away it's not arithmetic, because if I go from 100 to 20, I'm going to subtract. I'm going to subtract, what, 80? And then going from 20 to 4, I would subtract 16. So I'm not subtracting the same number each time. For geometric, what would we do? So what would we multiply 100 by to get 20? Well, again, a way that you can do this is you could take 20 divided by 100, and that would give us, what, 1 over 5, so 1/5. So we multiply by 1/5 to go from 100 to 20, and that's not a very good multiplication symbol there. Let me fix that. I don't really like to use times symbols because they look like X's, but I will here because that star didn't look very good. So let's see, what do we multiply 20 by to get 4? Well, let's just try 1/5. 20 times 1/5 would be 20 divided by 5 or 4, so 1/5 works here as well. And then does that work going from 4 to 0.8? Well, let's see, if we take 4 times 1/5, that would be equal to 4/5, and that, whoops, sorry, wrote the wrong number there. That would be equal to 4/5. That's the same as what over 100? It'd be the same as 80 over 100, which is 0.8. Okay, so we got it. We found that our common ratio here is 1/5, and that tells us that this sequence is going to be geometric. We multiply by the same number each time we go from one term to the next. And usually when a sequence is geometric, we would also make a note here that we know that's because our common ratio here is 1/5. All right, let's go on. Number 7. Determine whether the sequence is arithmetic, geometric, or neither. We have 9/4, 1, -1/4, -3/2. Oh my goodness. Well, let's see what let's start with arithmetic. I usually start with arithmetic. Most times it's simpler. I don't know that it looks that much simpler here, but let's try it. What number would I add to go from 9/4 to 1? Well, I could find that by taking 1 minus 9/4, which would be 4/4 minus 9/4, or -5/4. Okay, so we're subtracting 5/4 to go from 9/4 to 1. Let's see what happens when I go from 1 to -1/4. Well, that would be 4/4. That would be, if we want to find the difference, we'd take -1/4 minus 1. That would be -1/4 minus 4/4, and that also would be -5/4. So we're good so far. Let's try this third, going from the third term to the fourth term. And if I took -3/2 minus a -1/4, that would be -6/4 plus 1/4, and again we'd have -5/4. So once more we add a -5/4 to go from -1/4 to -3/2, and so actually we found that the sequence is arithmetic with a common difference of -5/4. All right, once we find it's arithmetic, of course we did find a sequence a bit ago that was arithmetic and geometric, but generally if it has the word or in here, we're going to assume that we don't get more than one here. But you could try on your own to determine if this could be geometric by going from one term to the next, do you multiply by the same number each time? But for now, I'm going to go on to problem number 8. We're going to find the sum of this arithmetic sequence, the sum from k equals 1 to 29 of k plus 1 over 4. So the sum of an arithmetic sequence is one of these formulas you should know. The sum of the first n terms of an arithmetic sequence is equal to n over 2 times the first term plus the last term, or the nth term. Okay, so this would be a finite arithmetic series that we're looking at, and we go from k equals 1 to 29. Well, that tells me that I'm finding the sum of the first 29 terms, so I'm going to plug in 29 for n, and then I just need to get my first term plus the last term. So right here, well, actually, we're working with k in this case, so I could say that a sub k is going to equal k plus 1 over 4. So if I want to find a sub 1 here, we're going to plug in 1 for k, and we get 2/4, which we could write as 1/2. So our first term, a sub 1, is equal to 1/2. Our a sub nth term, which in this case is going to be the 29th term. Our 29th term would be equal to 29 plus 1 over 4. That would be 30 over 4, and that would simplify to 15 over 2. So I have 15 over 2 here. Then we simplify. We have 29 halves times 1/2 plus 15 halves would be 16 halves. I could write 16 halves as 8. So, and then if we'd have 29 times 4, if we take 8 divided by 2, 29 times 4 then is going to be equal to 116, if I did that right. Let me check my notes here. Yeah, that looks right. Okay, 116. So we have the sum of that arithmetic sequence. And it wouldn't hurt to go ahead and write out a few terms here to see what's going on, to verify that it's an arithmetic series. Okay. So an arithmetic series is just the sum of the terms in a sequence, right? Okay, and here we're finding the sum of the geometric series. Well, for a geometric series, if this is written in summation notation, I'm going to strongly recommend that you do write out a few terms. So let's go ahead and write out some terms here. We have the sum from k equals 1 to infinity of -3 times 1/4 raised to the k minus 1. So each term is going to come from right here, and we're going to start with k equals 1. So to write out a few terms, our first term would be -3 times 1/4 raised to the 1 minus 1. And I think I'll put these in square brackets as we go along. A series, we add our terms as we go along. Our second term, we're going to go up one integer from k, so we're going to go to k equals 2. We'd have -3 times 1/4 raised to the 2 minus 1. And then our third term, let's do 3, and then I think we'll be good here. We're told that it's geometric, so maybe just do 3 as a check. So we have -3 times 1/4 raised to the 3 minus 1. And then we could keep going. Whoops. Let me go back there. And then we'd have plus and so forth. And here we'd keep adding these forever. There's no stopping place if we have an infinity on the top of our summation sign. So our first term would be what? -3 times 1/4 raised to the power of 0. Well, that's just going to be 1. Okay, so this is our first term. Our second term would be -3 times 1/4 raised to the power of 1, which would be 1/4. Our third term is -3 times 1/4 squared. That would be 1 over 16, and so forth. So we're going to have negative 3 plus a negative 3/4 plus a negative 3/16 plus, and so forth. So can you see what the common ratio is here? Well, first of all, I'm going to actually look for the first term. So to find the sum of this geometric sequence, or this geometric series, we would have our first term is negative 3. We can see the first number in our series is negative 3. And then to find the common ratio, what number do we multiply to go from negative 3 to negative 3/4? You can kind of look at this, hopefully, and see that the common ratio is going to be 1/4, also going from the second to the third term here. If you wanted to find that, just take any term, divide it by the previous term. Negative 3/4 divided by negative 3 would be negative 3/4 times 1 over negative 3, and we'd end up with positive 1/4 there. Okay, so we can see the common ratio is 1/4. What we're really interested in this problem, though, is to find the sum. The sum of an infinite geometric series is equal to a sub 1 over 1 minus r. We have a sub 1, we have r. The one thing we do need to check is that if a geometric series has a finite sum, if an infinite geometric series has a finite sum, it has to be true that our r value is between negative 1 and 1. It is here, so that checks. We're good with the r value. So we should have a finite sum for this infinite geometric series. So let's see what that would be. Well, a sub 1 is equal to negative 3, and r is equal to 1/4. So we're going to have negative 3 divided by 3/4. So that would be the same as negative 3 over 1 times 4 over 3. And we'd end up with a sum of this geometric series being negative 4. All right, so if we added these terms together forever, we would eventually get to negative 4. Let's go on to number 10 here. The seats in a movie theater are designed so that the first row contains 30 seats. The first row has 30 seats. The second row contains 32 seats, and each successive row contains 2 additional seats. If the theater has 40 total rows of seating, how many seats are in the theater? So we're going to think of this as an arithmetic problem where a sub 1 is the number of seats in our first row, which is 30. Our common difference is going to be the number of seats that we add as we go to the next row, the next row. Each time we go to a new row, how many seats do we add? And we're given that that is 2 here. We're also told the theater has 40 total rows, which is going to be our n for this problem. And so to find, what are we trying to do? We're finding the sum of the seats in the theater. So the sum of all our seats, S sub n, this is another formula you should know. So this formula is the sum of the terms in a finite arithmetic sequence is going to be n over 2 times the first term plus the last term in our sequence. So what do we know here? Well, we know that n is equal to 40. We know that a sub 1 is 30. What we don't know is what our last term is, which would be a sub 40. Okay, so to find our 40th term, another formula you should know is that a sub n equals a sub 1 plus n minus 1 times our common difference d. In this case, we're trying to find a sub 40. So we're just going to plug in 40 for n here. We also know that our first term is 30, so we have a sub 40 equals 30 plus 30 times our common difference d, which is 2. We are going to end up with a sub 40 is equal to 30 plus 60, or 90. So going back to our formula for finding our sum of the seats in the first 40 rows, we'd have 20 times 30 plus 90. We have 20 times 120. And so that would be what? 2400, 2,400 seats. And that doesn't look right. I think I've made a mistake somewhere. What did I do here? Okay, so, oh, I see what I did. Okay, so let's go back here. 40 minus 1 is not 30. What is 40 minus 1? It should be 39. Okay, so we have 30 plus 39 times 2. So that would be 30 plus 78. We should get a sub 4 is equal to 108. Okay, well that changes my work over here. It's good I worked this one out before. I might totally mess this up, huh? Okay, so let's just try that again. Okay, so we have 30 plus 108. 30 plus 108 would be 138. 20 times 138 is 2,760. So in the theater, there are 2,760 seats, which it's a good idea to double check your work. So if you're taking an exam and you get to the end and you have extra time, it always is a good idea to kind of backtrack there. The next thing we're looking at is expanding binomials. I use Pascal's triangle for expanding binomials, and so we'll use that here. This binomial is 3x minus 2 raised to the 4th power. We want to expand this. I'm going to start by making a sketch here of Pascal's triangle, which hopefully you've already practiced. And we're going to raise to the 4th power, we're going to go down to the 5th row. The 5th row in Pascal's triangle is 1, 4, 6, 4, 1. Okay, so using that 4th row, we're going to expand this binomial. The first thing I'm going to do is I'm going to rewrite my binomial as 3x plus a negative 2 raised to the 4th power. And now as I expand, I'll have 3x minus 4, 3x minus 2, raised to the 4th power equals, I'm going to grab this first one here in Pascal's triangle, the 5th row. I have 1 times, I'm going to then have 3x raised to some power times negative 2 raised to some power, and I move on to the second number in this 5th row of Pascal's triangle, which is a 4, and I will have 4 times 3x raised to some power times negative 2 raised to some power. I'll come back in just a minute and plug in those powers. Then we move on to 6. We have 6 times 3x raised to a power times negative 2 raised to a power. We move on to 4, where we have plus 4 times 3x raised to a power times negative 2 raised to a power. And then we have, last of all, 1 times 3x raised to a power times negative 2 raised to a power. And then for those powers, my binomial is being raised to the 4th power, so I will start with 3x to the 4th, and then I'm just going to go drop by one integer as I move along. 3x to the 4th, 3x cubed, 3x squared, 3x to the 1st power, 3x to the 0 power. With the negative 2, I'm going to do the opposite. I'm going to start with negative 2 raised to the 0, then to the 1st, then to the 2nd, then to the 3rd, and finally to the 4th. Okay, so I think I'm ready for, I put this on 2 slides because sometimes this takes up a lot of space, although we probably could have done this here. But let's go ahead with what we have and go ahead and move to my next slide here, where this is written out. So 3x minus 2 to the 4th power equals, and let's just start working this. We have 1 times 3x to the 4th. So 3x to the 4th would be 3 to the 4th times x to the 4th times negative 2 to the 0 is just going to be 1. And then we have plus 4 times 3 cubed times x cubed times negative 2 to the 1st power, which is negative 2. Then we have plus 6 times 3 squared times x squared times negative 2 squared, which is just positive 4. Then we have plus 4 times 3 times negative 2 cubed, which would be, it would be negative because it's an odd power, and, well, sorry about that. 2, 4, 8, it would be negative 8. And then we have plus 1 times 3x to the 0, which is 1, plus negative 2 to the 4th, which would be positive 2, 4, 8, 16. Okay, I probably could have worked with the 3's too as I went along, but let's go back and grab 3 to the 4th is 3, 9, 27, 81. So we have 81 times x to the 4th plus, well, this is going to be what? Let me simplify a bit as I go along here. So I'm going to have minus 8. 4 times negative 2, it gives us minus 8 times 3 cubed, which is 27. And then we have x cubed. Next we have plus 4 times 6 is 24 times 3 squared is 9 times x squared. And then we're going to have minus, oh, I forgot an x here, didn't I? So let me fix that. We have plus 4 times, let's just clean this up a bit. We have plus 4 times 3 raised to the 1st power times x, and then times negative 2 cubed, which would be negative 8. Okay, so now for this term, 4 times negative 8 would give us negative 32. Negative 32 times 3x, and then plus 16. So we have 81 x to the 4th minus 8 times 27, which would be 216. Oops. X cubed, and then we have plus 24 times 9 is also 216. X squared, and then we have minus 32 times 3 minus 96x plus 16. Okay, so this would be the expanded form of that binomial, and this is by far the easiest way to expand a binomial as far as I'm concerned. You could always do it term by term, but I think that would be quite a bit more work. But I'm going to point out something before we go on to our next slide. If I can hit the right button here. Notice that in any one term, if you add these two exponents together, you get 4, right? That's going to come into play in our next problem that we do here. So add the exponents together in any one term and you get 4. Okay, so let's go on to our next and last problem for today. This is a little bit shorter chapter than some. In number 12, we want to find the term containing x cubed in the expansion of 2x plus y to the 6th power. So if we expand 2x plus y to the 6th power, we'd have 2x plus y in our expansion. And if we use Pascal's triangle, we'd need to go down to the 7th row. So let's just jot down the rows of Pascal's triangle. 1, 1, 1, 1, 2, 1, 1, 4, 6, 4, 1, 1, 5, 10, 10, 5, 1. And let's see, we're on the 1, 2, 3, 4, 5, 6. This is the 6th row. We need one more row to give us the 6th power. We need the 7th row, which is 1, 6, 15, 20, 15, 6, and 1. And you can use the binomial theorem on this, but I think it's easier in the long run to remember Pascal's triangle. And this is a trick that you're going to want to use every once in a while in your future math career. So let's go ahead and look at the term containing x to the third. So for x to the third, if I take 2x and I raise 2x to the third power, that's the term from which I'm going to get x cubed, right? So let's think. Our first term here is going to be if we take 2x raised to the sixth power, the second term would come from 2x raised to the fifth power, and then we'd have 2x raised to the fourth power, and then next, this fourth term, we're going to have 2x raised to the third power. That's the power that I want in order to get the term containing x cubed. So we want this fourth term here, where we're going to have 20 as our term containing x to the cube. We're going to start by using Pascal's triangle to get a coefficient of 20 here. And then we're going to take 20 times 2x raised to some power times y raised to some power. Well, remember, we're at this term where we raise 2x to the third power. And from the last example that we looked at, notice that the sum of our exponents on the 2x and the y need to add to 6. That tells me that I need a 3 here so that I have this term to the powers that it needs to be. So that gives me 20 times 2 cubed times x cubed times y cubed. We just have to simplify here. So we're going to have 20 times 8 x cubed, y cubed. 20 times 8 would be 160. And so we end up with our term containing x to the cube is going to be 160 x cubed, y cubed. And that would be our last problem for today. So you can also review the worksheet for this section and ask me any questions that you have as you're getting ready for this next exam. So best of wishes, and thanks for hanging out here today.